Thank you so much for the invitation. It's so glad to be here in front of my colleagues, and thank you, Professor Zhang and all the professors for the invitation. So today I'm going to talk about a research topic that I've been working on about now like 4 or 5 years from my PhD and my postdoc. That's about deep generative models, which is a new type of modeling framework using neural networks, and especially how I kind of use those kind of models for transportation and mobility data. So for those of you who don't really know me, I'm an assistant professor at the University of Minnesota. I started this semester. I just finished my first semester there. So I did my bachelor, master, PhD at KAIST in Department of Civil and Environmental Engineering with Professor Pasu Yo. And I did a postdoc with Professor Lee Jun-soon here at McGill University for about 2 years. And this year, January, I joined University of Minnesota. So my research focus is on AI for transportation systems. And within that scope, I study urban transportation mobility data, spatial temporal data analytics, and some connected automated vehicles and cooperative ITS. So my research is focused on data. So when we talk about data, we have to really understand what we can get from data. So we collect data from real world, and we try to, so any type of research process, we try to make a model that describes the data. But what do we really want to do with the model? So in my opinion, I think we develop model to create or generate synthetic data so that we can understand the real world better. So one example is we have a highway traffic data, and then we collect like microscopic trajectory data or macroscopic traffic flow data, and then we come up with traffic flow theory, microscopic driving behavior models, and so on. And then we build a traffic simulator, which can also generate new data that we want to simulate. So simulation is a way we kind of use to generate new data under new scenarios. So in this sense, we are doing the same understanding of the data. So by using the data, we are trying to create a model, and then we are using the model to create another synthetic virtual data so that we can understand our transportation system better. So my definition of data is that we have real world and data, and we can treat this real world as a distribution. And we collect samples, the data samples from this distribution. And what we do is we use the data to understand the distribution. And so as a researcher, when we deal with data, we try to, or we want to learn, understand the distribution of the data by using the samples from that distribution. So there are many ways we can kind of learn how to learn the distribution from the samples. One of the simplest idea is that we assume a probabilistic distribution, like in a statistical approach. Say we assume that the distribution is going to follow some Gaussian distribution or binomial distribution, and then we try to estimate the parameters of the distribution. But sometimes these kind of models have a really good interpretability and really good mathematical framework, but their capability of describing diverse distribution is kind of limited. So one of the new approaches that tries to deal with estimating the distribution is that we train a neural network that can produce similar properties to the given data. So this is a new idea that came around, say, 20 years ago or 10 years ago, and people call it deep generative models. And nowadays, because of ChatGPT and other types of generative type of modeling approach, people call it generative AI, but I do prefer to call it deep generative models. So to kind of get some sense of what this deep generative model is, we have to go back to the categories of machine learning. So in machine learning, we usually have three things: supervised learning, unsupervised learning, and reinforcement learning. And when you take a first course for your machine learning, I think supervised learning and reinforcement learning kind of describes itself, but it's really inconvenient and kind of gray to understand what unsupervised learning is. So supervised learning, we have input data and label, and we learn the transformation or a function that maps the input data X to a label Y. So for example, we have classification where we learn the decision boundaries between the two data classes, or we have object detection, semantic segmentation, or we have some forecasting or imputation task. So in this type of problems, we have a input data and we have a desired outcome. And also in reinforcement learning, we have a different modeling framework. We have a state action reward. So we try to learn a function, or we call it policy in reinforcement learning, that maps the state to the action to maximize the expected cumulative maximize expected reward. So in this case, we are trying to do some kind of control task. So in this case, sequential decision making really matters. So this is a really short abstracted description of supervised and reinforcement learning. So, but when I first heard the term unsupervised learning, it was very kind of vague to me. So we have data X, but we don't really have a label, right? And when you look at the definition of unsupervised learning, it tells you that you try to learn some underlying structure of the data, and that doesn't really describe anything. And if you go into the examples, you can see some clustering, density estimation, and feature learning or dimensionally reduction. So now you kind of get some sense that, so we have the data, but we try to understand what's in the data and how this data kind of operate by itself. And one of the approach in unsupervised learning is deep generative model. So the goal of deep generative model is to train a model. So given a training data drawn from some distribution, we train a neural network or a model that estimates the distribution directly, or we estimate the likelihood directly, or we learn the capability to generate new samples from the same distribution. So say we have the training data colored in blue. We try to train a neural network that produce realistic samples that's similar to the original data distribution. So in today's talk, I'm going to give you 2 example studies I did for about 4 or 5 years. So first one focusing on the generation part. So generating new types of new samples from the same distribution. And I'm going to present about this trajectory model that I developed while I was a PhD student at KAIST. And I'm going to show how I generated new synthetic trajectory data. And then in the second part of the talk, I'm going to focus more on the density estimation, estimating the distribution itself. And I'm going to show conditional normalizing flows for estimating the distributions for microscopic trajectories for pedestrians and aircraft and so on. So I was not a little bit, but very interested in trajectory data when I was a PhD. And my whole PhD dissertation was about trajectory data. So trajectory data can be defined as a movement of different agents in the city, including vehicles and pedestrians. And this type of data is widely, so I started this project, this study in 2017. Back then it was not very common, but nowadays it's very common to collect this kind of data. So we have GPS, Bluetooth, Wi-Fi, and other types of sensors that we can collect a lot of trajectory data. And when you look at this individual trajectory, you can identify where this person or vehicle came from, the origin, and where it's going to the destination. And also we can identify the route choice behavior, how much travel time it took, the average link flow, and so on, average link travel time, and so on. But when you collect a massive amount of trajectory data and form a group of trajectories, this group of trajectories kind of represent collective mobility behavior of the urban network. So when you look, so if you look at the right video here, you can identify where are the crowded area, how is the flow between the regions, change over time, how is the origin destination distribution change over time, and so on. So, so, so this type of data can give us a huge understanding of how we can use huge understanding of urban transportation network and the behaviors of the agents in this urban transportation network. So I was interested in this trajectory data, and one of the topics I did was to reproduce and recreate synthetic vehicle trajectory data so that we can use it for other type of mobility data analytics. But this ability to reproduce realistic trajectories of individual agents was also a key interest of transportation engineers for many, many years. But in the past, because we could not really actually observe those trajectory data, we relied on traditional network flow models. Say we have trip generation and we have origin and destination. We have route choice models based on logits or other types of choice behavior models. And we use simulation, traffic simulation, either microscopic or macroscopic simulation. And then we get a simulated trajectory, and then we hope that the simulated trajectories can represent the unobserved trajectories. But if you're a little bit familiar with traffic simulation, you can see that this model itself has a lot of limitation because there are a lot of different assumptions in model building process and calibration processes. And there are strong behavior assumptions such as agents always follow the shortest path, or they follow some certain type of distribution for route choice behavior. And also traffic simulation models like CTMs have simplified physical processes which are good in terms of computation, but may impact the outcome in terms of trajectory. So now we have actually, we now have the actual ability to observe the real trajectory data. And then we have seen an outstanding performance of data-driven approaches and learning-based approaches based on neural network. So my idea was, can we actually generate new synthetic trajectories, not relying on any type of behavior assumptions, and develop a model that can capture the nonlinear spatial temporal features in the data set. So, that's why I came up with this trajectory model. So I'll kind of walk you through step by step how I kind of made my ideas and developed the model. So before my study, so I had another paper too, and then there were many other studies that tries to generate or predict the trajectory. And the usual way they do is they have a sequence of previously visited locations, and they predict the next location step by step, and then create a vehicle trajectory. But when you kind of, and they use RNN or other sequence-based neural network models to embed the information from the sequence of previously visited locations to predict the next steps. But when you think about this, we can see that so every time you make a prediction, you will have some kind of error, and this error can be accumulated as the trajectory goes. So when you have a full trajectory data generated, you are going to see a huge discrepancy between the real trajectories and the predicted or generated trajectories by this approach. So one of my core idea was that I wanted to incorporate the distribution of expected future trajectories and have some kind of multimodality into the modeling framework. But I thought that maybe if I don't consider the previously visited location, this model might be limited. So the core idea of my model was I combined a recurrent neural network, RNN, to embed the sequence of previously visited locations, and generative adversarial imitation learning, which is one deep generative model, one example of deep generative model, to incorporate the distribution of expected future trajectories together so that I can create and reproduce realistic trajectories. So in a nutshell, this is a whole modeling framework I had. It looks very complicated. But in the core, we have this RNN layer here, which embeds the previously visited locations and this policy generator and a whole other neural network together kind of helps this policy generator to create new trajectory. And GALE, or Generative Adversarial Imitation Learning, is a modeling framework founded on imitation learning. And imitation learning is also known as learning from demonstrations. So given expert demonstration, so we have real-world data as expert demonstration, the goal is to train an agent to mimic the behaviors of the expert. So in early days, this imitation learning was used for robotics and in mechanical engineering applications. So if you have an expert demonstration of your hand picking up an apple, a robot can imitate your actions and decision-making process to pick up an apple. But then the application area has been expanded to human behavior modeling. So I use this modeling framework to understand and imitate the decision-making process that people have in route choice and trip generation, and so on. And GALE, Generative Adversarial Imitation Learning, is a combination of generative adversarial networks with imitation learning or inverse reinforcement learning. So here we have two neural networks. One is called generator, and the other is discriminator. So we create this generated samples from generator, and this discriminator distinguishes whether this generated sample distinguishes the generated samples from the real samples. So this generator and the discriminator have this competitive framework, so that as the training goes, generator tries to generate more and more realistic samples, while discriminator tries to distinguish the realistic samples from the real samples. So that by doing this competition, both neural network will kind of improve its capabilities, and then eventually we are going to have a really good generator that discriminator cannot really distinguish between those two. So to kind of give you a direct example to understand it better, so we have an agent, a vehicle that's choosing its route in Gangnam network or a given traffic network. And the state can be defined as current and previously visited locations. And we have actions of the link-to-link transition actions such as turn left, go straight, turn right, and terminate the trip. And we feed in the trajectory data as input as expert demonstration, and we train the neural network to imitate the decision-making process of the trajectory in the trajectory data so that we can generate realistic trajectories. And I use two types of data. One is generated by Aimson traffic simulator. This was to kind of have a proof of concept using a simple data set. So I used 3 different OD matrices described here and 5 different routing algorithms. So in total, I had 15 different data sets. And I used a real-world collected Gangnam data set from Seoul taxi DTG data. I extracted taxi trajectories from this Gangnam network here so that I have a real-world observed trajectories. And one of the key things I did in this study was that I wanted to have a really good performance evaluation framework. So I divided the evaluation into 2 steps. The first one was trajectory level evaluation. So when you think about generating trajectory, you want the generated trajectory by itself to be realistic. But also, when you have a collective trajectory, generated trajectory data, you want this data set itself to have the similar mobility patterns as the real given trajectory data set. So I divided the evaluation into 2 parts. First one was trajectory level evaluation. So we want the trajectory to be realistic as an individual agents, individual trajectory. And we have this data set level evaluation. So we want the trajectory data set or the group of trajectories to represent the overall trajectory mobility behavior in the urban transportation network. So this is the first result in the trajectory level evaluation. I used two different measures from sequence modeling area called BLUE and Meteor. So you can see that the purple bar indicating the performance of the proposed model was way better than conventional models like mobility Markov chain, RNN, and maximum entropy models. And especially in the Gangnam experiment, it showed that so not only this has a big, it has better performance in terms of the average score, but it also has a small standard deviation. So this means that the proposed model can generate realistic, so in trajectory level, it can generate realistic samples, and also it can generate those realistic samples in a stable way, so that we don't really have a much difference, so we don't really have a big standard deviation in the scores. Also, in the data set level results, I used a distribution, so a measure to quantify the difference between these two distributions, which is Jensen-Shannon distance. So this is lower the better. So if this value is 0, two distribution has the same distribution, and if it's 1, it's completely different. And then because I had 16 different data sets, I made this chart to demonstrate. So as the complexity of the data set increases, I wanted to see how the model reacts to the complexity of the data set. And you can see that here, the purple line indicating the proposed model is more robust than compared to other models, because even though the complexity of data set increases, the performance drop is not significant compared to other models. So to kind of summarize the first part, so I developed a trajectory model for generating and reproducing realistic mobility behavior and realistic mobility trajectories. And there can be many different applications, such as it can be used to resolve the privacy issues which is prevalent in trajectory data. Also, it can be used for data augmentation for trajectory data or other types of data. And then we can use the augmented data set for training other neural networks. Also, so specifically for this model, because this is generating origin and destination and route choice behavior, given the trajectory data, it can replace the routing engines for traffic simulators. And also nowadays, so this model is kind of assuming that all trajectory are equally counted. But in some settings, we want to kind of augment some data, and then so that we have a actual distribution of trajectory. So for example, like say in the States, because we have like diverse demographic distribution and in spatially and in terms of race and everything, in terms of race and income and everything, by combining the trajectory data and the household survey or other type of data sources, and then if we can kind of augment some data so that we can kind of overcome the bias in the data set, we can use those kind of trajectory data for decision making for traffic transportation policy implementation and so on. So that's one of the research I'm currently doing on this direction. So for the second study, so this was the study I started when I was a postdoc at McGill University. So after my PhD, I was more interested in microscopic trajectories. So usually we had this ngSim data that's collected in 2004 or 5, and that kind of opened the new doors for analyzing traffic, like microscopic driving behaviors and so on. And nowadays there are many drone-based data or other fixed camera sensor data to collect trajectories of pedestrians and vehicles, so that we can understand how driving behavior change in different traffic settings, how pedestrians make the decisions, and then how vehicles and pedestrians interact with each other. So there must be a video running here. But, oh, okay. So from this kind of data, we can understand those kind of behaviors. And I wanted to try if I can make a model that learns the distribution of pedestrian movement and other vehicle movement. So the core idea was that given some trajectory data, we want to predict some kind of future trajectory. So the conventional way of microscopic trajectory prediction is that we do a deterministic prediction. So as an outcome, we have a single line trajectory in the red area. But my approach was that I wanted to model a distribution of future trajectory because the nature of microscopic trajectory is that, especially for pedestrians and especially for vehicles in the at intersection or roundabouts, they don't really have a fixed Gaussian-based distribution, but they have really somewhat crazy distributions. So I wanted to capture whether this distribution would help us to understand the behaviors of pedestrians better. So the problem formulation is that we want to learn the conditional distribution of future trajectory given the past trajectory. And the modeling framework I used here is called normalizing flows, and it's also called as flow-based generative models. So the core idea is that we start from this simple known distribution, and we learn some kind of transformation function from this simple distribution to the complicated distribution. And another core idea is that so when we do this kind of learning this kind of transformation, we have this type of encoder and decoder type of modeling setup. So, but in normalizing flows, we assume that this encoder and decoder is inverse function relationship. So we assume that decoder is an inverse function of encoder and encoder is an inverse function of decoder. And by using that, we can come up with really good mathematical derivation of finding the actual distribution without losing any type of information. So compared to other deep generative models like variational autoencoder and generative adversarial network, by using this framework, we can estimate the likelihood function itself directly without any assumption. But so this is the good part, but we have a huge disadvantage in terms of selecting the right structure because the function itself should be invertible. And if we follow our math courses in middle school and high school, we know that invertible functions are not easy to find. So for trajectory prediction, so probabilistic trajectory prediction setting, I had this previously visited location or previous trajectory as input. So we have the coordinates or speed, acceleration, heading, and agent classes such as pedestrian and vehicle. So we can come up with some kind of condition encoder. Say we have RNN or transformer to encode the information we have in the given trajectory. And then we use normalizing flows so that we can model the distribution of future trajectory X given the observation and feature we have O and F. So this is one work I'm still working on with one of the master students at University of Minnesota. So this is one preliminary result we have. So here we have a blue line here, which is the given trajectory. And the red line here is the ground truth trajectory that this agent really took. And we can see a video of this contour map indicating the distribution of this vehicle's location at each time step. And so one of the interesting things was that, so in the early time steps, we can kind of assume that they are following some kind of Gaussian distribution because we have a really centered Gaussian type of distribution. But as the time goes, we see that we have a wide range of this area. So, and this also makes sense because based on this trajectory, we cannot really determine whether this vehicle is going to turn left or go straight. And this distribution can capture those kind of behavior too, and then have a wide range of prediction in terms of distribution. Also, in this case, we have a right-hand vehicle, and we already see a lot of, so we already see right-hand movement here, so the model can capture that this vehicle is going to go in this direction, so we have more like a Gaussian type of distribution. So I'm kind of expanding this study to apply this framework for monitoring intersection safety. And also, so if we have two agents like this, and then we have an overlapping distribution map, we can quantify how likely those two agents are going to collide. And based on that, we can understand how they interact with each other and how they change their behavior based on those kind of collision probability given by interacting with each other. And another study I have is the one I'm doing with researcher at Korea Transport Institute. So we are looking at the distribution of conventional aircraft. So here, so in this map, we have Incheon Airport. So this is Seoul, and we have Incheon Airport here, and we have Seoul City Center here. So they're trying to build air taxi or UAM system between Incheon Airport to Seoul. But as we all know, we have Gimpo Airport, which creates a lot of aircraft trajectories. And it would be nice if they just follow the fixed route, but because of the weather and the airport traffic condition and so on, they have a huge uncertainty in terms of trajectories. So it is the key, so one of the key idea is that we can, if we can predict, so because of this, so the air taxi should kind of bypass this whole region to the north and then get closer to North Korea, which is not really ideal. Or we should go to the south and then make a big detour. So one of the core ideas was that if we can accurately predict the distribution of trajectories and use that for decision-making process for controlling EV tolls, we can kind of have like shorter route without losing too much. So here we have red trajectory as a given trajectory, blue trajectory as a brown choice trajectory, and green ones here are the predicted samples created by the train. You can see that they are predicting pretty well, and this is better than deterministic forecasting, because if the deterministic forecasting fails, the outcome of this failure is critical. But if we have a distribution of trajectories and we have a lot of samples, diverse samples that can kind of simulate how this vehicle is going to move in the future, we can kind of use some kind of control algorithm, and we can also use the likelihood of that trajectory so that we can decide how we should react to those kind of circumstances. So we are kind of using deep generative model as some kind of simulator for the aircraft. So here on the right, we have the videos of a sample control scenarios. So we have the red dots here, which is the conventional aircraft, airplanes, and the green one here is the air taxi. And because it knows the distribution of trajectory, it can kind of pass through even though the aircraft is coming closer. So in summary, this two ideas I have is using conditional normalizing flows for predicting and generating the distribution of microscopic trajectories. And I think there can be a lot of different applications from this. I'm using it for intersection trajectory prediction and modeling interaction behaviors between agents, and also using it for predictive airspace allocation and predictive control for EV tolls. But if you think about it, there can be a lot of different applications from this. So the last slide, I want to kind of give you some ideas I have right now. So what are the challenges and next steps that we have to care about? So one thing is that we really have to care about scalability, because if you talk about distribution, you're adding a huge complexity level to the model. So, and then we know that the distribution can be affected by a lot of different external factors, and how to incorporate those external factors efficiently without losing too much in terms of computation complexity is one of the key things we have to deal with to develop a better model. And also, this is actually the core scope I have, the core direction I have right now is that, so how can we ensure that the trained model work with the out of distribution cases? So especially, it's especially important in transportation engineering, because we know that the behaviors of the people or behaviors of the vehicles and pedestrians change over time, because they adapt to new environment. And even though we have a fixed origin and destination, we can change our mode of transportation, we can change the route we are taking. So how can we kind of adopt this dynamic type of distribution by using the generative model? Say we trained one deep generative model in 2018, and then we had a COVID strike, which is way out of distribution for us. Can we use the same model for COVID case that's trained on non-COVID scenarios? So that's one direction I have right now. And also, it's kind of connected, can we use DGMs, deep generative models, for what-if scenarios? So one of the reasons we use traffic simulation a lot is because we can simulate what-if scenarios. So what if this link is blocked? What if we have a new bridge here? So can we do those kind of reasoning and those kind of analysis by using data-driven deep generative models? So, and then I think the core idea here is to identify causality from the data. So what causes what, and what's the outcome of what. And then if we can identify those kind of causality, we can kind of have simulate the what-if scenarios. And then we can maybe have a fully data-driven traffic simulator with high fidelity accuracy and so on by using like a lot of data collected from urban transportation network. So yep, this is it for this session. So if you have any questions, I'm welcome to take any questions.
If anyone have a question, please hands up. I'll pass you the mic.
Thank you for the nice presentation. And my name is Tenfen Ling, and I'm also very interested in generative models. So I'm very interested in the topic you are talking about, the what-if situation. So I also have this kind of inspiration when the first time that I check with the stable diffusion and I get in touch with the conditional generative models. And at that times, there are more and more research these days. They are trying to extract the information from the data set with the spatial and temporal information, utilizing some designed encoders as conditional embeddings to the generative models for the what-if scenarios for this achievement. For example, like this year, especially for the stable diffusion, they're trying to interface more information from the stable temporal information that we embedded. They designed for some encoders for that. So my question is, what do you think of like this kind of the future of this kind of methodology? Because if we are trying to utilize this kind of like embedding technology, which means that we are trying to represent these explainabilities of the transportation into another kind of neural networks. So in that ways, it will lack of the like explainabilities compared with the original data-driven traffic simulator. So what do you think of like the comparison of we'd rather need to utilize another kinds of like neural network for the spatial temporal information embedding, or we need to discover another way? For example, like this year PASI paper about another paper which is utilizing a combination of the diffusion model and the fundamental diagrams for the noise cancelling by Professor Weima. And I'm wondering like which kind of like tendencies do you prefer, and what is your opinion about that?
So there are many ways that we can try to overcome the what if scenario cases, and we can definitely add more neural networks for conditional encoder, but that also relates to the scalability issue, because if we have one external outcome, external factor we want to incorporate, and then we train another neural network for that, and then what if we have another kind of external factor we want to include? We need to train it again, and then that's going to cost a lot of money in terms of training and collecting the data. So that's one way, and there's a lot of different researchers who's working on that. But what I'm focusing is what's fundamentally related to what if scenario. So that's why I kind of mentioned the causality, because as a human, we kind of understand what causes what, because if we have a new bridge there, that causes the behavioral change of the users, and then we kind of, even though we don't have a concrete like causal diagram, but we kind of understand how this process goes internally in our mind and collectively as a society. So if we can identify those kind of structure, causal structure, and then if we can incorporate that, or if we can let DGMs to learn those kind of causal structure by itself, I think it's going to be more flexible to those kind of new what-if scenarios that we are interested in. So, and this is also a really active area of research in transportation and also in AI field. So there are a lot of different ideas coming up nowadays to identify the causality. So if you're interested, you can kind of use the keyword and then try to search for some papers related to this direction.
Thank you for answering.
I'm also very interested in the deep generative model, so thank you for your great presentation. I may start to ask an easy question. How do you think about the relationship between the generative AI foundation models such as ChatGPT with the deep generative models? Is it an expanded version of deep generative model? I want to hear from your understanding.
Yeah, that's a really hard question as a new faculty, because there are a lot of debates about that. So my perspective is that ChatGPT is a very early stage of the deep generative model. So there are a lot of different types of deep generative model. So in the second session, I'm going to have a tutorial session with code of 2 deep generative models. But the earliest deep generative model was autoregressive generative model. So we sample one data at a time. So what ChatGPT is doing is just predicting the next word. And when we go back to this, so ChatGPT is predicting the next steps. But as a whole trajectory, we might have some kind of discrepancy as a trajectory, or as a sentence, or as a paragraph. But ChatGPT is using huge computational resource and a lot of data and a really deep transformer to kind of overcome this limitation. So that's one way, but there can be another efficient way of using already discovered different types of generative models so that we can have a better predicted or generated results. So there can be 2 different types of.
Okay.
And recently, Professor Yan Lu-kun from NYU kind of commented on new researchers in AI that they should not focus on large language models and focus more on like fundamental generative model. But there are a lot of other researchers who are working on large language models. And I also see a lot of huge potential from large language model too. So I think both directions are valid, but it depends on your opinion and your data and your application of interest.
Oh, thank you for your answer. I have another question. Could you explain the discriminator in your training again? Because I want to have better understanding.
So maybe in the second session, I'm going to explain it in more detailed way. So you can think of this as the money counterfeiter and the police officer. So if you think, so the counterfeiter is going to try to generate like fake money, and then police officer is going to capture that fake money and then distinguish the fake money from the real money. And this is like really widely used example explaining generative adversarial network. So as this competition between counterfeiter and the police officer kind of continues, the counterfeiter is going to generate really realistic fake money that discriminator or police officer cannot really distinguish. So that eventually we want the generator to generate realistic samples. So we have this like game theoretic competitive framework. So these two neural networks are competing each other so that it can improve its capability better and better as the training goes. But there are some disadvantages of this framework because of the nature of this competitive framework, maybe this may not represent a real distribution or something like that.
Okay, thank you.
And thank you for your clear and interesting lecture. And I have a question about the prediction of microscopic trajectory. So I know that there are several researches to predict future trajectory using graph-based AI techniques considered a neighbor vehicle's trajectory, like graph attention network. And how do you think about this technique compared to your proposed method?
So currently, I'm not looking at the so maybe I should switch to this slide. Oh. So currently, I'm not looking at the information from the neighboring agents. So that's a two different direction we have in the trajectory prediction area. So there are some people who are focusing more on multi-agent prediction. So that which means that we incorporate the information from different agents, surrounding agents, and then either we predict this ego vehicle or ego agent's trajectory, or we predict the multi-agent trajectory as a whole. And my research is more on we focus on one agent and we try to predict the distribution of this ego agent. And also this can be expanded to the multi-agent scenarios where we have more and more x's, say we have x1 to xn, but that's going to be a huge joint distribution, which is not usually easy to train. So that's one direction I'm working on right now. So it's a different direction, but it can be combined. So in short, I think that's the answer.
Yeah, thank you for good answer.
Thank you. I wanted to ask you about the causal learning structure.
Sorry?
Causal learning?
Causal? Yep.
Yes. In my understanding, that requires the assumptions between the features, finding the features. What if some kind of changes in inputs or features, what affects, how it would be different, right? So I think the prior assumptions that we're gonna find is quite important to start the research about the causal learning. So what do you think is the best way to build some assumptions between the features, and how can you apply it to, for example, in your trajectory predictions?
So even in the recent research, they are using some kind of synthetic data first. So they have a really strong causal graph first, and then they generate new data from there. And then they try to develop a model, say a neural network that can identify those causal graph structure that kind of generated the data set. But in real world, we don't, so sometimes we have those kind of strong causal relationship, but usually we don't really have like really strong, but we have a like middle to strong range of causal relationships. So identifying causality in real world is much more challenging than identifying those well-established causal structure. So I don't really have a right answer right now because I'm still working on it. I'm still studying about it, but I think it's a good way to start. And but causal inference itself in transportation engineering has been studied in a very long period. Say in 1970s, 80s, 90s, if you find some papers, especially in traffic safety, there are some papers that tries to identify the causal structure between the crash probability and some kind of road geometry and so on. So maybe we can start from there, and then we can collect some data with the same with a similar environment, and then if we can identify those kind of causal structures that's known in transportation engineering, that's going to be a good start. And maybe if we can kind of expand that idea to general settings, say traffic speed prediction and like congested cases, say can we kind of identify like causal graph between the link in the highway? So can we kind of make a causal graph for, so if location A kind of gets congested, what's the causal relationship between that to being location B being congested? So can we kind of identify those kind of causality? So this is, I think this is still really open topic right now, and I don't see a lot of researchers talking about this yet, in transportation at least. So maybe this is a good time for you to kind of dive in and then study more about this.
Thank you.
Thank you so much for the talk. I understand parts of it. I don't understand other parts. Again, for those of you who don't know already, but I've said this numerous times, I'm a social scientist, and my job is to annoy the engineers as much as possible. So I'm wondering, because your unit of analysis is individual agents, have you ever thought about privacy issues related to that? Because I deal with AV policy, and one of the things that we're really concerned about is privacy of AVs and road conditions and the pedestrians who have not consented to their data being collected. And even if they have consented, they may not understand the implications of that consent. So how do you deal with that problem?
So privacy and data ethics, and especially AI ethics, is one of the key things I'm always concerned about, because one of the core application I kind of proposed for my first study is that we can use it for resolving the privacy issue, because we need, so as engineers, we need a lot of data so that we can understand the situation and the problem better. But then this type of trajectory data has a lot of information that we can use, but they are not really easily accessible because they have those kind of privacy sensitive information. Even though those users kind of has consented to the data collector, but they didn't consent to the data users like us, so that the data collector cannot kind of distribute this type of data publicly. But if we have some kind of like sensor data, and if we can use that as a preliminary research for developing new mobility, say policy implementation, I think it's going to be very good. But so what I'm claiming is this type of generative approach can be used to overcome that limitation. So the data collector can use the generative models to provide a synthetic data so that they can test their model in a synthetic scenario first. And then if they have some kind of good outcomes, and then they have a solid ideas and examples of how this trajectory data or how this privacy sensitive data can be used to improve the overall system in transportation, I think we can start a new process of collecting. That's going to be the reasoning of collecting a new data with consent to use those data for those kind of policy implementation. And I think it's a really big issue nowadays, because people are all concerned about being our data used, say, in ChatGPT or other generative models. So as a researcher, I try to be very conservative about that, and then try not to make any kind of problem from other from the data provider or the users. So I hope I answered the questions correctly.
So I think we have to finish now for some break time.
Yeah.
And then during the break, Seongjin may answer to your individual questions, right?
Okay.
So we are resting, you are not. Okay, thank you.